In single variable calculus, we hunt for local extrema in 2 steps. Find where f' of c is 0, then check the sign of f" of c. Positive second derivative means local minimum, negative means local maximum, 0 means the test bails out. Today we promote that recipe to surfaces. A smooth function, f of xy, has a horizontal tangent plane exactly when both partials vanish, which is to say, when the gradient is the 0 vector. Those are the critical points, the only candidates for interior local extrema. But 2 dimensions opens a new possibility that 1 dimension never had, the saddle point, where the surface curves up in one direction and down in another. We need a finer test, and the test is built from the 3-second partials packaged into a 2x2 Hessian matrix. Its determinant D equals f sub x times f sub iy minus f sub xy squared, together with the sign of f sub xx, classifies the critical point. We'll prove the rule from Taylor's theorem, work 3 examples, 1 minimum, 1 saddle, and 1 cubic with both, and connect it back to the 1 variable case by showing that positive definite Hessian is the right multivariable spelling of f" of c greater than 0. By the end, you should be able to take any polynomial in x and y, find its critical points, and classify them inside of a minute. Quick recap from single variable calculus. Step 1. Find critical points by setting f' of c equal to 0. Step 2. Check f" of c. If it is positive, the graph is locally a parabola opening upward, so c is a local minimum. If f" of c is negative, the parabola opens downward and c is a local maximum. If f" of c is 0, the test is inconclusive and we go hunting with higher derivatives or a sign change of f'. The reason it works is Taylor's theorem. Near a critical point, the linear term vanishes, so the leading behavior of f is the quadratic 1/2 f" of c times h squared. The sign of f" of c tells you whether that quadratic is a smile or a frown, which tells you the local shape of the graph. Today we generalize this to surfaces, and we'll see that the right object is not a single number, but a 2x2 matrix. A local maximum on a surface is a point where the surface peaks compared to its immediate neighborhood. F of a, b is at least as large as f of xy for all xy nearby. A local minimum is the same idea with the inequality flipped. So far, this is the obvious lift from one variable. The new phenomenon, with no one-dimensional counterpart, is the saddle point. A saddle is a place where the surface goes up in one direction and down in another, so it is a critical point but not an extremum. The cleanest example is f of x, y equals x squared minus y squared at the origin. Walk along the x-axis, where y equals 0, f of x, 0 equals x squared, a parabola opening up, so we climb. Walk along the y-axis, where x equals 0, f of 0, y equals negative y squared, a parabola opening down, so we descend. The origin is simultaneously a minimum along one axis and a maximum along the other. It cannot exist in one dimension because there are not 2 independent directions to walk. Our test has to detect this third possibility. The first step in the multivariable extremum hunt is to find the critical points. An interior point AB is critical when either both partials vanish at the same time, the gradient is the 0 vector, or one of the partials fails to exist. The geometric content of the gradient of f equals the 0 vector is clean. From last episode, the tangent plane has slope f sub x in the x direction and f sub y in the y direction. If both are 0, the tangent plane is horizontal. A horizontal tangent plane is the multivariable version of a horizontal tangent line in one dimension. The multivariable Fermat's theorem says, at an interior local extremum, the gradient must vanish. So critical points are the only candidates, but, as in one dimension, not every critical point is an extremum. Saddles are critical points too. The gradient test screens for candidates. We need a second test to decide what kind of critical point each candidate is. Practical note, solving the gradient of f equals the 0 vector is a system of 2 equations in 2 unknowns, which can have anywhere from 0 to many solutions, possibly with messy algebra. That is one of the genuine new complications of the multivariable problem, but it is also where most of the interesting structure lives. Here is the test, the centerpiece of today's episode. Take a critical point, A, B, and compute the 3-second partials f sub x, 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 f sub y, y, and f sub x, y, all evaluated at A, B. Form the number D, which is the product of the 2 pure second partials minus the square of the mixed partial. D equals f sub x, x times f sub y, y, minus f sub xy squared. Then read off the classification. If D is positive and f sub xx is positive, you have a local minimum. The surface is bowl-shaped, with both principal curvatures positive. If D is positive and f sub xx is negative, you have a local maximum, the same bowl shape, but flipped upside down. If D is negative, you have a saddle. The surface curves up in one direction and down in another. And if D equals 0, the test cannot decide. The quadratic part of the surface is degenerate, and you need other tools, like a higher-order Taylor expansion or a direct comparison along curves. Quick note, When capital D is greater than 0, the equation forces f sub xx times f sub yy greater than f sub xy squared, which is at least 0, so f sub xx and f sub yy must have the same sign. You can check either one to decide max versus min, and they will always agree. The mixed partial f sub xy enters squared, so its sign doesn't matter. Only its magnitude does, and that magnitude is what can drag capital D down into negative territory and turn a would-be extremum into a saddle. Where does this come from? Taylor's theorem. Near a critical point, the linear part of f vanishes because the gradient is 0, so the Taylor expansion starts at second order. F of a plus h, b plus k is approximately f of a, b plus 1/2 of the quadratic form f sub x x times h squared plus 2f sub xy times hk plus f sub y times k squared. That quadratic form Q of h, k, governs the local shape. To see what shape, complete the square. Assuming f sub xx is not 0, you can write Q as f sub xx times the quantity h plus f sub xy over f sub xx times k, all squared, plus a second term whose coefficient is exactly D over f sub xx multiplied into k squared. Now read off the signs. If D is greater than 0, the two squared coefficients are f sub xx and D over f sub x, which have the same sign as f sub xx. So Q is everywhere of one sign. Always non-negative if f sub xx is greater than 0, always non-positive if f sub xx is less than 0. That's a bowl, open up or open down. If D is less than 0, the two squared coefficients have opposite signs, so Q takes positive values in some directions and negative values in others. That's a saddle. The whole test is one application of completing the square. Here are the three local shapes side by side. On the left, a local minimum, the surface is a bowl opening upward, and every slice through the critical point is a parabola curving up. The Hessian determinant D is positive. Both pure second partials are positive, and f sub xx is positive, confirming the upward bowl. In the middle, a local maximum, same bowl shape, flipped upside down. D is still positive, because flipping both signs of f sub xx and f sub yy leaves the product unchanged, but now f sub xx is negative. On the right, the saddle, the surface rises in one direction and falls in the perpendicular direction. A vertical slice along one axis is a parabola opening up. The slice along the other axis is a parabola opening down. The Hessian determinant is negative because f sub xx and f sub yy have opposite signs, or because the mixed partial f sub xy is large enough to dominate. Three shapes, one number to distinguish them. First worked example. Take f of x, y equals x squared plus y squared minus 4x minus 6y plus 13. Step 1. Find critical points. The gradient is the vector with components 2x minus 4 and 2y minus 6. Setting both components to 0 gives x equals 2 and y equals 3, so there is a single critical point at 2, 3. Step 2. Compute second partials. F sub xx equals 2, f sub yy equals 2, f sub xy equals 0. There is no cross term in the original function. Step 3. Form D, it's 2 times 2 minus 0 squared, which is 4, which is positive. Since D is positive and f sub xx equals 2 is positive, the critical point is a local minimum. The value of the function there is 4 plus 9 minus 8 minus 18 plus 13, which is 0. As a sanity check, completing the square shows that f of xy equals the quantity x minus 2 squared plus the quantity y minus 3 squared, a paraboloid centered at 2, 3 with its vertex at height 0, opening upward. The minimum we just found by the test coincides with the bottom of the bowl, as it should. Second worked example, with the cleanest saddle in mathematics. Take f of x, y equals xy. Gradient. The gradient of f is the vector with components y and x. Set both components to 0, and we get y equals 0 and x equals 0, so the only critical point is the origin. Second partials, f sub xx is the derivative of y with respect to x, which is 0. F sub yy is the derivative of x with respect to y, also 0. F sub xy is the derivative of y with respect to y, which equals 1, or equivalently the derivative of x with respect to x, also 1. So the Hessian determinant is 0 times 0 minus 1 squared, which equals -1 negative. The test calls this a saddle. We can double check by walking along two lines through the origin. Along the line y equals x, the function becomes x times x, which is x squared, which is non-negative and equals 0 only at the origin. So along that direction, the origin is a local minimum. Along the line y equals -x, the function becomes -x squared, which is non-positive and 0 only at the origin, a local maximum along that direction. Min in one direction, max in another in every neighborhood. That is exactly a saddle point, and the test detected it from a single determinant. Third worked example, a meteor one, f of xy equals x cubed minus 3xy plus y cubed. The gradient is the vector with components 3x squared minus 3y and 3y squared minus 3x. Setting both components to 0 is a small system. The first equation says y equals x squared. The second says x equals y squared. Substitute the first into the second. X equals the quantity x squared, which is x to the fourth, which rearranges to x to the fourth minus x equals 0, or x times the quantity x cubed minus 1 equals 0. The factors give x equals 0 or x equals 1. From y equals x squared, the corresponding y values are 0 and 1. So there are two critical points, the origin, 0, 0, and the diagonal point, 1, 1. Already this is richer than the single variable analog. We have a system of two equations to solve, and the algebra delivers more than one candidate point. The next step is to classify each one using the second partials test. Now classify both critical points. The second partials of f equals x cubed minus 3xy plus y cubed are f sub xx equals 6x, f sub yy equals 6y, and f sub xy, the derivative of negative 3x with respect to y. Wait, careful, f sub x equals 3x squared minus 3y. So f sub xy is the derivative of f sub x with respect to y, which is negative 3. Same number from the other order by clear out. At the origin, f sub xx equals 0, f sub yy equals 0, and f sub xy equals negative 3. The Hessian determinant is 0 times 0 minus negative 3 squared, which is negative 9, negative. So the origin is a saddle point. At the point 1, 1, f sub xx equals 6, f sub yy equals 6, and f sub xy equals negative 3 as before. The Hessian determinant is 6 times 6 minus negative 3 squared, which is 36 minus 9, which is 27, positive. Since capital D is greater than 0 and f sub xx equals 6 is positive, 1 is a local minimum. The value of f there is 1 minus 3 plus 1, which is negative 1. One function, two critical points, one of each kind. This is the kind of multi-critical point hunt that single variable calculus cannot prepare you for, and the Hessian test handles it in a few lines of arithmetic. Let me reveal the structure behind the test. Package the 3 second partials into a 2x2 matrix called the Hessian, with f sub x, x, and f sub y on the diagonal and f sub xy off the diagonal in both positions. It is symmetric, because f sub xy equals f sub yx whenever both are continuous by Clairaut's theorem. The determinant of this matrix is f sub xx times f sub yy minus f sub xy squared, which is exactly our capital D. The whole test, dressed up in linear algebra, is a statement about whether the Hessian matrix is positive definite, negative definite, or indefinite. Positive definite means the associated quadratic form, H transpose times capital H times H, is strictly positive for every non-zero vector H, which geometrically means the second-order Taylor expansion is a bowl opening up in every direction, a local minimum. Negative definite means the same expression is always negative, a local maximum. Indefinite means the quadratic form takes both signs, a saddle. And degenerate means the determinant is 0, the matrix has a kernel, and the test is silent because the quadratic part fails to control the shape. This is the multivariable generalization the linear algebra people have been waiting for. Let me make the bridge to single variable calculus completely explicit. In one variable, f double prime of c greater than 0 is the condition for a local minimum at a critical point. If we view f double prime of c as the unique entry of a 1x1 matrix, then positive number and positive definite matrix mean exactly the same thing. In two variables, we generalize positive to positive definite, a property of 2x2 symmetric matrices. By Sylvester's criterion, a 2x2 symmetric matrix is positive definite if and only if its determinant is positive and its top left entry f sub x is positive. Those are exactly the two conditions in our test for a local minimum. The same story carries on to n dimensions. The Hessian becomes an n by n symmetric matrix of all the second partials, and positive definite is still the condition for a local minimum, checked by all n leading principal minors being positive. So the second partials test is not a special trick for two variables, it is the dimension, two instants of a clean linear algebra dichotomy that runs all the way up. Recap. A critical point of a smooth function f of xy is where both partials vanish, the gradient of f equals the 0 vector, or where a partial fails to exist. Geometrically, the tangent plane at a critical point is horizontal. To classify the critical point, compute the 3 second partials and form the Hessian determinant capital D equals f sub x, x times f sub iy minus f sub xy squared. If capital D is greater than 0 and f sub xx is greater than 0, it's a local minimum, bowl opening up. If capital D is greater than 0 and x of xx is less than 0, it's a local maximum, bowl opening down. If capital D is less than 0, it's a saddle, one direction up, another down. If capital D equals 0, the test is inconclusive and you need finer tools. The deeper view is in linear algebra. The test is a check on whether the Hessian matrix is positive definite, negative definite, or indefinite. We worked 3 examples: a shifted paraboloid with a single minimum at 2, 3, the function xy with the cleanest saddle at the origin, and the cubic x cubed minus 3xy plus y cubed with 2 critical points, a saddle at the origin and a local minimum at 1. Next episode, we add a constraint. The unconstrained problem asks where the surface is flat. The constrained problem will ask where the surface is flat relative to a curve. That's Lagrange multipliers. That's the second partials test. One gradient equation to find candidates. The interior critical points where the gradient of f equals the 0 vector. One determinant, capital D equals f sub x times f sub x y minus f sub x y squared to classify them, plus the sign of f sub x to break the tie between minimum and maximum when capital D is greater than 0. The same construction extends to any number of variables under the heading positive definite Hessian, so what you've learned here is dimension 2 of a much larger story. If this helped, like, subscribe, and post a comment with your answer to today's challenge. Classify all critical points of f of x, y equals x to the 4th plus y to the 4th minus 4xy plus 1. There are 3 real critical points, and one of them is a saddle. Find them all and run the test. Next episode, we put a constraint on the problem. Instead of looking for the lowest point on the whole surface, we ask for the lowest point on the surface subject to a side equation like g of x, y equals 0. The geometry shifts beautifully. At the constrained extremum, the gradient of f is parallel to the gradient of g. That's the Lagrange multiplier method, and it's where unconstrained calculus meets the real world. See you there! A point A, B in the interior of the domain of f is a critical point when del f of AB equals 0, i.e. both partials vanish, or when one of the partials fails to exist. Geometrically, the tangent plane is horizontal. The surface has momentarily flat ground. To classify such a point, we form the Hessian determinant d equals fxx of AB fy of AB minus Spiegel fxy of AB egar squared, and consult the second partials test. dw0 with fxxw0 gives a local minimum, dwew0 gives a local maximum, dw0 gives a saddle point, d equals 0 is inconclusive. The deeper picture is linear algebra. The test asks whether the Hessian matrix is positive definite, bowl up, negative definite, bowl down, or indefinite saddle. We'll find the unique minimum of a shifted paraboloid, see f of xy equals xy saddle at the origin, and chase down both critical points of the cubic x cubed minus 3xe plus y cubed. Next episode, we release the surface from the open plane and trap it on a constraint curve. Lagrange multipliers handle extrema subject to g of xy equals 0 by demanding del f be parallel to del ge. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.